About a month ago, I was firmly recommended the Google Spanner paper as a starting point for distributed systems. And it's something that I've always been recommended and told that is really good. And it's a foundational paper in distributed systems. And I need to get smarter about distributed systems. So I figured I keep putting it off basically. I've already put this off for more than a month. And I think that the only way I'm going to do this is I'm going to read it, like literally verbally out loud. So this is an experiment. I have this recorded in video and audio form. So you're welcome to follow along, or of course, if you don't like audio or video, you can just read the paper. It's publicly available. So before I get into this, I think I'll just not read the footnotes and I'll just read the actual text. I might pause for some comments, or I might reread some sections that are hard to process. I think this will take roughly an hour based on the word count. I don't know if it'll actually be an hour. Yeah, well, one final fun fact. I just noticed his name, Hong Yi Lee. That is actually the the son of the Prime Minister of Singapore. And I did not know that he was involved in Spanner. So that's pretty impressive. Okay. Spanner, Google's globally distributed database. Abstract. Spanner is Google's scalable, multi-version, globally distributed, and synchronously replicated database. It is the first system to distribute data at global scale and support externally consistent distributed transactions. This paper describes how Spanner is structured, its feature set, the rationale underlying various design decisions, and a novel time API that exposes clock uncertainty. This API and its implementation are critical to supporting external consistency and a variety of powerful features. Non-blocking reads in the past, lock-free read-only transactions, and atomic schema changes across all of Spanner. 1. Introduction. Spanner is a scalable, globally distributed database designed, built, and deployed at Google. At the highest level of abstraction, it is a database that shards data across many sets of Paxos, state machines, in data centers spread all over the world. Replication is used for global availability and geographic locality. Clients automatically failover between replicas. Spanner automatically reshards data across machines as the amount of data or the number of servers changes, and it automatically migrates data across machines and even across data centers to balance load and in response to failures. Spanner is designed to scale up to millions of machines across hundreds of data centers and trillions of database rows. Applications can use Spanner for high availability even in the face of wide area natural disasters by replicating their data within or even across continents. Our initial customer was F1, a rewrite of Google's advertising backend. F1 uses 5 replicas spread across the United States. Most other applications will probably replicate their data across 3 to 5 data centers in one geographic region, but with relatively independent failure modes. That is, most applications would choose lower latency over higher availability, as long as they can survive 1 or 2 data center failures. This makes a lot of sense. Spanner's main focus is managing cross-data center replicated data, but we have also spent a great deal of time in designing and implementing important database features on top of our distributed systems infrastructure. Even though many projects happily use Bigtable, we have also consistently received complaints from users that Bigtable can be difficult to use for some kinds of applications, those that have complex, evolving schemas, or those that want strong consistency in the presence of wide area replication. Similar claims have been made by other authors. Many applications at Google have chosen to use Megastore because of its semi-relational data model and support for synchronous replication, despite its relatively poor write throughput. As a consequence, Spanner has evolved from a Bigtable-like version key-value store into a temporal multi-version database. Data is stored in schematized semi-relational tables, data is versioned, and each version is automatically timestamped with its commit time. Old versions of data are subject to configurable garbage collection policies, and applications can read data at old timestamps. Interesting. Spanner supports general-purpose transactions and provides a SQL-based query language. So I should probably disclose that this is one of the reasons I'm very interested in this is that I now work at a distributed database kind of company. We do use a database under the hood, so it's not really exactly similar, but we do perform a lot of these functions. So I'm trying to get smart on what the prior art is. Okay, back to reading. As a globally distributed database, Spanner provides several interesting features. First, the replication configurations for data can be dynamically controlled at a fine grain by applications. Applications can specify constraints to control which data centers contain which data, how far data is from its users to control read latency, how far replicas are from each other to control write latency. Wow, that is cool. And how many replicas are maintained to control durability, availability, and read performance. This is very, very concise stuff. Like within this one sentence, sets up a lot of requirements that people are going to need, and I really like it. Data can also be dynamically and transparently moved between data centers by the system to balance resource usage across data centers. Second, Spanner has two features that are difficult to implement in a distributed database. It provides externally consistent read and writes and globally consistent reads across the database at a timestamp. Yep, okay. These features enable Spanner to support consistent backups, consistent MapReduce executions, and atomic schema updates, all at global scale, and even in the presence of ongoing transactions. Okay, yeah, because he used a timestamp. These features are enabled by the fact that Spanner assigns globally meaningful commit timestamps to transactions, even though transactions may be distributed. The timestamps reflect serialization order. In addition, the serialization order satisfies external consistency, or equivalently, linear realizability. If a transaction T1 commits before another transaction T2 starts, then T1's commit timestamp is smaller than T2's. Spanner is the first system to provide such guarantees at global scale. It doesn't seem like such a big deal, but I think I've heard of the synchronizing atomic clock problem, so I figure that that's how it does it. Let's see. The key enabler of these properties is a new TrueTime API and its implementation. The API directly exposes clock uncertainty, and the guarantees on the guarantees on Spanner's timestamps depend on the bounds that the implementation provides. If the uncertainty is large, Spanner slows down to wait out that uncertainty. Holy shit. Google's cluster management software provides an implementation of the TrueTime API. This implementation keeps uncertainty small, generally less than 10 milliseconds, by using multiple modern clock references, GPS and atomic clocks. Section 2 describes the structure of Spanner's implementation, its feature set, and the engineering decisions that went into their design. Section 3 describes our new TrueTime API and sketches its implementation. Section 4 describes how Spanner uses TrueTime to implement externally consistent distributed transactions, lock-free read-only transactions, and atomic schema updates. Section 5 provides some benchmarks on Spanner's performance and TrueTime behavior and discusses the experiences of F1. Sections 6, 7, and 8 describe related and future work and summarize our conclusions. Section 2, Implementation. This section describes the structure of and rationale underlying Spanner's implementation. It then describes the directory abstraction, which is used to manage replication and locality, and is the unit of data movement. Finally, it describes our data model, why Spanner looks like a relational database instead of a key-value store, and how applications can control data locality. A Spanner deployment is called a universe. Given that Spanner manages data globally, there will be only a handful of running universes. We currently run a test/playground universe, a development/production universe, and a production-only universe. What's a development/production universe? I don't understand that. Spanner is organized as a set of zones, where each zone is the rough analog of a deployment of Bigtable servers. Am I supposed to look at figure 1? No, I guess, okay, yeah. So let me try that again. Spanner is organized as a set of zones, where each zone is a rough analog of a deployment of Bigtable servers, okay? Zones are the unit of administrative deployment. The set of zones is also the set of locations across which data can be replicated. Zones can be added to or removed from a running system as new data centers are brought into service and old ones turned off respectively. Zones are also the unit of physical isolation. There may be one or more zones in a data center, for example, if different applications' data must be partitioned across different sets of servers in the same data center. Figure 1 illustrates the servers in a spanner universe, which is a very simple chart with zone 1, zone 2, zone n. Pretty simple. A zone has one zone master and between 100 to several thousand span servers. The former assigns data to span servers. The latter, span servers, serve data to clients. So a zone master is like a router, I guess. The per zone location proxies are used by clients to locate the span servers assigned to serve their data. The per zone location proxies are used by clients to locate the span servers assigned to serve their data. The universe master and the placement driver are currently singletons. Okay, that's singletons. These are outside the system of a spanner organization. The universe master is primarily a console that displays status information about all the zones for interactive debugging. The placement driver handles automated movement of data across zones on the timescale of minutes. The placement driver periodically communicates with the span servers to find data that needs to be moved, either to meet updated replication constraints or to balance load. For space reasons, we will only describe the span server in any detail. I'm going to try that again. The placement driver handles automated movement of data across zones on the timescale of minutes. The placement driver periodically communicates with the span servers to find data that needs to be moved. Okay, so it's like a worker that just like looks for rebalance opportunities. And a universe master is a console, so it's like a web UI. Why don't you just call that instead of these weird names? Anyway, section 2.1, talking about span server, the span server software stack. This section focuses on the span server implementation to illustrate how replication and distributed transactions have been layered onto a Bigtable-based implementation. The software stack is shown in Figure 2. Let's look at Figure 2. Figure 2 has a bunch of data centers, and each of them has a replica. They communicate with Paxos, and below that there's a tablet and this Colossus. And one of the data centers is a leader. And on top of the leader, they're responsible for a group, and they can communicate with other groups. Between that, the leader's responsibility are to have a lock table and have a transaction manager. So let's see what that is. So at the bottom, each span server is responsible for between 100 and 1,000 instances of a data structure called a tablet. A tablet is similar to Bigtable's tablet abstraction in that it implements a bag of the following mappings. So it's a mapping from key string in timestamp of int64 to string. So it's a function or a mapping. Unlike Bigtable, Spanner, so it's like a tuple of key and timestamp, and then it maps to a string. Okay. Unlike Bigtable, Spanner assigns timestamps to data, which is an important way in which Spanner is more like a multi-version database than a key value store. So yeah, it's not key mapping to string, it's key and timestamp mapping to string. The tablet state is stored in a set of B-tree-like files in a write-ahead log, all on a distributed file system called Colossus, the successor to Google File System. To support replication, each span server implements a single Paxos state machine on top of each tablet. An early Spanner incarnation supported multiple Paxos state machines per tablet, which allowed for more flexible replication configurations. The complexity of that design led us to abandon it. Okay, so only one state machine on top of each tablet. Each state machine stores its metadata. Sorry about that. I'm going to pause and make sure that I have my alarms turned off. These are just in case I overslept for like productivity. Okay. Each state machine stores its metadata and log in its corresponding tablet. How many tablets are there? There are 100 to 1,000. Yeah, 100 to 1,000 instances of a data center. Okay. Why all these weird names? Our Paxos implementation supports long-lived leaders with time-based leader leases, whose length defaults to 10 seconds. Wow. The current Spanner implementation logs every Paxos write twice. The current Spanner implementation logs every Paxos write twice. once in the tablet's log and once in the Paxos log. The choice was made out of expediency, and we are likely to remedy this eventually. All implementation of Paxos is pipelined, so as to improve spanner throughput in the presence of WAN latencies. But writes are applied by Paxos in order, a fact on which will depend in section 4. Okay. The Paxos state machines are used to implement a consistently replicated bag of mappings. The key value mapping state of each replica is stored in its corresponding tablet. Writes must initiate the Paxos protocol at the leader, reads access state directly from the underlying tablet and any replica that is sufficiently up to date. The set of replicas is collectively a Paxos group. At every replica, there is a leader. In every replica that is a leader, each span server implements a lock table to implement concurrency control. So here we're talking about the leader specific attributes. The lock table contains the state for two-phase locking. It maps ranges of keys to lock states. Note that having a long-lived Paxos leader is critical to efficiently managing the lock table. In both Bigtable and Spanner, we design for long-lived transactions, for example for report generation, which might take on the order of minutes, which perform poorly under optimistic concurrency control in the presence of conflicts. Operations that require synchronization, such as transactional reads, acquire locks in the lock table. Other operations bypass the lock table. Oh, wow, that's pretty smart. Okay. Here we go. At every replica that is a leader, each span server also implements a transaction manager, so that's up here above the log table, to support distributed transactions. The transaction manager is used to implement a participant leader. The other replicas in the group will be referred to as participant slaves. I bet they changed that. If a transaction involves only one Paxos group, as is the case for most transactions, it can bypass the transaction manager, very smart, since the lock table and Paxos together provide transactionality. If a transaction involves more than one Paxos group, those groups' leaders coordinate to perform two-phase commit. Yeah, okay. One of the participants' groups is chosen as the coordinator. The participant leader of that group will be referred to as the coordinator leader, and the slaves of that group will be coordinator slaves. The state of each transaction manager is stored in the underlying Paxos group, and therefore is replicated. So careful. Section 2.2, Directories and Placement. On top of the bag of key value mappings, the Spanner implementation supports a bucketing abstraction called a directory, which is a set of contiguous keys that share a common prefix. The choice of term directory is a historical accident. A better term might be bucket. We will explain the source of that prefix in section 2.3. Supporting directories allows applications to control the locality of their data by choosing keys carefully. A directory is the unit of data placement. All data in a directory has the same replication configuration. When data is moved between Paxos groups, it is moved directory by directory, as shown in figure 3. So here we look at figure 3. Yep, it moves directories in groups. All right, cool. Okay. Spanner might move a directory to shed load from a Paxos group to put directories that are frequently accessed together into the same group, or to move a directory into a group that is closer to its accessors. Directories can be moved while client operations are ongoing. One could expect that a 50 megabyte directory can be moved in a few seconds. The fact that a Paxos group may contain multiple directories implies that a Spanner tablet is different from a Bigtable tablet. The former is not necessarily a single lexicographically contiguous partition of the row space. Instead, a Spanner tablet is a container that may encapsulate multiple partitions of the row space. We made this decision so it will be possible to co-locate multiple directories that are frequently accessed together. Oh. Okay, so it's like a suboptimal thing from the lexicographic sorting point of view, but actually co-locating multiple directories is more important, which is fair. Move dir is the background task used to move directories between Paxos groups. Move dir is also used to add or remove replicas to Paxos groups, because Spanner does not yet support in-Paxos configuration changes. Alright. Move.dir is not implemented as a single transaction, so as to avoid blocking ongoing reads and writes on a bulky data move. Instead, Move.dir registers the fact that it is starting to move data and moves the data in the background. When it has moved all but a nominal amount of the data, it uses the transaction to atomically move that nominal amount and update the metadata for the two Paxos groups. Okay. A directory is also the smallest unit whose geographic replication properties, or placement for short, can be specified by an application. The design of our placement specification language separates responsibilities for managing replication configuration. Do you have a language? DSL. Administrators control two dimensions: number and types of replicas, and the geographic placement of those replicas. They create a menu of named options in those two dimensions. For example, North America replicated 5 ways with 1 witness. An application controls how data is replicated by tagging each database or individual directories with a combination of these options. For example, an application might store each end user's data in its own directory, which would enable user A's data to have 3 replicas across Europe, and user B's data to have 5 replicas across North America. For expository clarity, we have oversimplified. In fact, Spanner will shard a directory into multiple fragments if it goes too large. Fragments may be served from different Paxos groups and therefore different servers. Move.dir actually moves fragments and not whole directories between groups. Oh, that's nice. That wasn't too bad. That was like 3 sentences. Okay. Section 2.3, Data Model. Spanner exposes the following set of data features to applications: a data model based on schematized semi-relational tables, a query language, and a general-purpose transaction. The move towards supporting these features was driven by manufacturers. The need to support schematized semi-relational tables and synchronous replication is supported by the popularity of Megastore. At least 300 applications within Google use Megastore, despite its relatively low performance. They really dunk Megastore because its data model is simpler to manage than Bigtables, and because of its support for synchronous replication across data centers. Bigtable only supports eventually consistent replication across data centers. Examples of well-known Google applications that use Megastore are Gmail, Picasa, Calendar, Android Market, and App Engine. The need to support a SQL-like query language in Spanner was also clear, given the popularity of Dremel as an interactive data analysis tool. Finally, the lack of cross-row transactions in Bigtable led to frequent complaints. Percolator was in part to address this failing. Some authors have claimed that general two-phase commit is too expensive to support because of the performance or availability problems that it brings. We believe that it is better to have application programmers deal with performance problems due to overuse of transactions as bottlenecks arise, rather than always coding around the lack of transactions. Running two-phase commit over Paxos mitigates the availability problems. The application data model is layered on top of the directory bucketed key value mappings supported by the implementation. An application creates one or more databases in a universe. Each database can contain an unlimited number of schematized tables. Tables look like relational database tables with rows, columns, and version values. We'll not go into detail about the query language for Spanner. It looks like SQL, with some extensions to support protobuf valued fields. Spanner's data model is not purely relational in that rows must have names. More precisely, every table is required to have an ordered set of one or more primary key columns. That's not purely relational? Ordered set. I think that's the key. It's an ordered set. Or is relational not restrictive of primary keys? I don't know. This requirement is where Spanner still looks like a key value store. The primary keys form the name for a row, and each table defines a mapping from the primary key columns to the non-primary key columns. Oh yeah. Isn't that how tables work? A row has existence only of some value, even if it is null. is defined for the row's keys. A row has existence only if some value, even if it is null, has defined for the row's keys. Okay. Imposing this structure is useful because it lets application control data locality through their choices of keys. Figure 4 contains an example spanner schema for storing photo metadata on a per user per album basis. So let's take a quick look at figure 4, which is down here. Figure 4, this is some SQL-like syntax. So it says create table users, UID int64 not null, email string, and then primary key UID, directory. Second table is create table albums, UID int64 not null, AID int64 not null, and name string. Primary key UID AID, interleave in parent users on delete cascade. Very concise. Very concise. Okay. The table at the top of the... Okay, so let's go back to... Figure 4 contains an example spanner schema for storing photo metadata on a per user per album basis. The schema language is similar to Megastores, with the additional requirement that every spanner database must be partitioned by clients into one or more hierarchies of tables. Client applications declare the hierarchies in database schemas via the interleave-in declarations. The table at the top of the hierarchy is a directory table. Each row in the directory table with key k, together with all the rows in descendant tables that start with k in lexicographic order, forms a directory. On delete cascade says that deleting a row in the directory table deletes any associated child rows. The figure also illustrates the interleave layout for the example database. For example, albums 2, 1 represents the row from the albums table for user ID 2, album ID 1. This interleaving of tables to form directories is significant because it allows clients to describe the locality relationships that exist between multiple tables, which is necessary for good performance in a sharded distributed database. Without it, Spanner would not know the most important locality relationships. All right, never seen that, but awesome. Okay, that's section 2. It described the data model, directories and placement. It described the span server software stack, and we know a little bit about how it transfers data and how the data persistence layer is the way I think about it looks. Uses fragments. The naming is all super weird, but it sounds fine. Data model is SQL-like, with some locality inserted into it. Okay. Hopefully that was not a terrible summary of a very complex paper. Section 3, true time. So here we have table 1, which we will talk about, I guess. Nothing here. So let's talk about true time. There's a simple table here. There are 3 methods in true time. So it's truetime.now, truetime.after, and truetime.before. So truetime.now refers an interval between the earliest time that we think now is and latest time that we think now is. Truetime.after is true only if t has definitely passed, and truetime.before returns true if t has definitely not arrived. Very simple. This section describes the TrueTime API and sketches its implementation. We leave most of the details for another paper. Our goal is to demonstrate the power of having such an API. Table 1 lists the methods of the API. TrueTime explicitly represents time as a TT interval, which is an interval with a bounded time uncertainty, unlike standard time interfaces that give clients no notion of uncertainty. The endpoints of a TT interval are of time or type TT stamp. The tt.now method returns a TT interval that is guaranteed to contain an absolute time during which tt.now was invoked. Yeah, oh, that's great. The time epoch is analogous to Unix time with leap second smearing. Define the instantaneous error bound as epsilon, which is half of the interval's width, and the average error bound as epsilon with a thing on top. I forgot what the epsilon bar. Okay. The tt.after and tt.before methods are convenience wrappers around tt.now. Fair enough. Denote the absolute time of an event epsilon e by the function t absolute e. In more formal terms, TrueTime guarantees that for an invocation tt equals tt.now, tt.earliest smaller than t absolute e of now smaller than tt.latest, where e of now is the invocation event. The underlying time references used by TrueTime are GPS and atomic clocks. TrueTime uses two forms of time reference because they have different failure modes. GPS reference source vulnerabilities include antenna and receiver failures, local radio interference, correlated failures, for example design faults such as incorrect leap second handling and spoofing, and GPS system outages. Atomic clocks can fail in ways uncorrelated to GPS and each other, and over long periods of time can drift significantly due to frequency error. Fuck. I have never worried about leap seconds in my life. TrueTime is implemented by a set of time master machines per data center and a time slave daemon per machine. The majority of masters have GPS receivers with dedicated antennas. Okay, alright. These masters are separated physically to reduce the effects of antenna failures, radio interference, and spoofing. The remaining masters, which we refer to as Armageddon masters, are equipped with atomic clocks. Ooh, that's a great name. An atomic clock is not that expensive. The cost of an Armageddon master is of the same order as that of a GPS master. All masters' time references are regularly compared against each other. Each master also cross-checks the rate at which its reference advances time against its own local clock. What? And evicts itself if there is substantial divergence. Each master also cross-checks the rate at which its reference advances time against its own local clock. How? What? Okay, so I don't understand what the reference is then. Between synchronizations, Armageddon masters advertise a slowly increasing time uncertainty. Oh, that's great. That is derived from conservatively applied worst-case clock drift. GPS masters advertise uncertainty that is typically close to zero. Man, alright, but you better be sure. Every daemon pulls a variety of masters to reduce vulnerability to errors from any one master. Some are GPS masters, chosen from nearby data centers. The rest are GPS masters from further data centers, as well as some Armageddon masters. How do you take into account speed of light speed? Daemons apply a variant of Marzullo's algorithm to detect and reject liars. Who's lying? And synchronize the local machine clocks to the non-liars. To protect against broken local clocks, machines that exhibit frequency excursions larger than the worst case bound derived from component specifications and operating environment are evicted. Whoa, alright, let's do that again. To protect against broken local clocks, machines that exhibit frequency excursions larger than the worst case bound derived from component specifications and operating environment are evicted. Wow. Okay, got it. Does some machine person said that? I don't know. Between synchronizations, a daemon advertises a slowly increasing time uncertainty. Epsilon is derived from a conservative, I thought we already read this, applied worst-case local clock drift. Epsilon also depends on time master uncertainty and communication delay to time masters. In a production environment, epsilon is typically a sawtooth function of time, varying about, why is it a sawtooth function? Varying from about 1 to 7 milliseconds over each pole interval. Epsilon bar is therefore 4 milliseconds most of the time. The daemon's pole interval is currently 30 seconds, and the current applied drift rate is set at about 200 milliseconds per second, which together account for the sawtooth bounds from 0 to 6 milliseconds. The remaining 1 millisecond comes from the communication delay to the time masters. Excursions from this sawtooth are possible in the presence of failures. For example, occasional time master unavailability can cause data center-wide increases in epsilon. Similarly, overloaded machines and network links can result in occasional localized epsilon spikes. Alright. Very, very low level. What do I learn from this? That's all of section 3. I mean, I just learned that the TrueTime API, uses two types of masters. The Armageddon master is kind of like the doomsday backup scenario, and then there's some kind of drifts that you model for. It increases over time. I like the GPS syncing. I think that's pretty cool. I don't think they really answered what happens with like the communication delay, as they call it. How come it's always 1 millisecond? I thought you dynamically speak to further data centers as well. So some questions unanswered about that, but I think the beauty of a constrained API is that all I need to know is that I can trust the TrueTime API. Hopefully they've done the math to make sure that the risk of getting this really wrong is very, very low. Section 4, concurrency control. This section describes how TrueTime is used to guarantee the correctness properties around concurrency control, and how these properties are used to implement features like externally consistent transactions, lock-free read-only transactions, and non-blocking reads in the past. These features enable, for example, the guarantee that a whole database audit read at timestamp t will see exactly the effects of every transaction that has committed as of t. Going forward, it will be important to distinguish writes as seen by Paxos, which we will refer to as Paxos writes, unless the context is clear, from spanner client writes. For example, two-phase commit generates a Paxos write for the prepare phase that has no corresponding spanner client write. What? Why? Alright, section 4.1, timestamp management. Table 2 lists the type of operations that Spanner supports. Let's look at Table 2. Table 2 lists 4 types of operations. One is read-write, second is read-only, third is snapshot read, client-provided timestamp, fourth is snapshot read, client-provided bounds. So read-write transaction is pessimistic, whereas read-only, snapshot read with timestamp and snapshot read with bound is lock-free. They're all lock-free except for the first one. And then I don't know this thing about replica required, so let's read on. The Spanner implementation supports read-write transactions, read-only transactions, pre-declared snapshot isolation transactions, and snapshot reads. Standalone writes are implemented as read-write transactions. Non-snapshot standalone reads are implemented as read-only transactions. What are snapshot? Non-snapshot standalone reads. So what are standalone reads? Okay, yeah, I think I get it. Both are internally retried. Clients need not write their own retry loops. That's pretty neat. A read-only transaction is a kind of transaction that has the performance benefits of snapshot isolation. A read-only transaction must be pre-declared so as not to have any writes. It is not simply a read-write transaction without any writes. Alright, big whoop. Reads in a read-only transaction execute at a system-chosen timestamp without locking, so that incoming writes are not blocked. Oh. The execution of the reads in a read-only transaction can proceed on any replica that is sufficiently up-to-date. A snapshot read is a read in the past that executes without locking. A client can either specify a timestamp for a snapshot read or provide an upper bound on the desired timestamp staleness and let Spanner choose a timestamp. Ooh, oh, that's a great API. In either case, the execution of a snapshot read proceeds at any replica that is sufficiently up to date. So every replica has a notion of like how up to date they are. And then you can just execute queries against that. Beautiful. For both read-only transactions and snapshot reads, commit is inevitable once a timestamp has been chosen, unless the data at that timestamp has been garbage collected. Okay, when does it garbage collect? As a result, clients can avoid buffering results inside of a retry loop. As a result, clients can avoid buffering results inside of a retry loop. When a server fails, clients can internally continue the query on a different server by repeating the timestamp and the current read position. Okay. Section 4.1.1, Paxos leader leases. This is going to be way out of my... All right. Spanner's Paxos implementation uses time leases to make leadership long-lived, 10 seconds by default. A potential leader sends requests for timed lease votes. Upon receiving a quorum of lease votes, the leader knows that it has a lease. A replica extends its least vote implicitly upon a successful write, and the leader requests least vote extensions if they are near expiration. Define the leader's least interval as starting when it discovers it has a quorum of least votes, and ending when it no longer has a quorum of least votes because some have expired. Spanner depends on the following disjointness invariant. Well, I don't know what the fuck that is. For each Paxos group, each Paxos' leader's least interval is disjoint from every other leader. Appendix A describes how this invariance is enforced. I am not reading that. Fuck it, I'm going to read it. Where's Appendix A? Appendix A, Paxos leader lease management. Okay. Yeah, it's a proof. It's a very short proof. We don't need to get into it, but all right. Okay, so back to section 4.1.1, Paxos leader leases. I'm going to continue where I stopped. The Spanner implementation permits a Paxos leader to abdicate by releasing its slaves from their least votes. To preserve the disjointness invariant, Spanner constrains when an abdication is permissible. Define S-max to be the maximum timestamp used by a leader. Subsequent sections will describe when S-max is advanced. Before abdicating, a leader must wait until after tt.after S-max is true. Yeah, fair enough. Assigning timestamps to RW transactions, read-write transactions. Transactional reads and writes use two-phase locking. As a result, they can be assigned timestamps at any time when all locks have been acquired, but before any locks have been released. For a given transaction, Spanner assigns it the timestamp that Paxos assigns to the Paxos write. That represents the transaction commit. Wow, very precise. All right, good. Spanner depends on the following monotonicity invariant. Within each Paxos group, Spanner assigns timestamps to Paxos writes in monotonically increasing orders, even across leaders. A single leader of replica can trivially assign timestamps in monotonically increasing order. This invariant is enforced across leaders by making use of this disjointness invariant. A leader must only assign timestamps within the interval of its leader lease. So very strict system. Wow. Note that whenever a timestamp S is assigned, S-max is advanced to S to preserve disjointness. Spanner also enforces the following external consistency invariant. If the start of a transaction T2 occurs after the commit of transaction T1, then the commit of timestamp of T2 must be greater than the commit of timestamp of T1. Define the start and commit events for transaction Ti by e start I and e commit I, and the commit timestamp of a transaction Ti by Si. The invariant becomes T absolute E1 commit is less than T absolute E2 start, which basically implies that S1 is lesser than S2, which is what we want for the monotonicity assurance. The protocol for executing transactions and assigning timestamps obeys two rules, which together guarantee this invariant as shown below. Define the arrival event of the commit request at the coordinator leader for a write Ti to be E server I. Start. The coordinator leader for write Ti assigns a commit timestamp Si no less than the value of TT now latest, computed after the E server I. Note that the participant leaders do not matter here. Section 4.2.1 describes how they're involved in the implementation of the next rule. The commit wait. The coordinator leader ensures that clients cannot see any data committed by TI until tt.after SI is true. Commit wait ensures that SI is less than the absolute commit time of TI, or SI less than T absolute E commit. Sorry, I'm reading on math. It's really stupid. Yeah, there's a start and there's a commit wait. All right, whatever. Section 4.1.3, serving reads and a timestamp. The monotonicity invariant describes in section 4.1.2 allows Spanner to correctly determine whether a replica state is sufficiently up to date to satisfy a read. Every replica tracks a value called safetime, tsafe, which is the maximum timestamp at which a replica is up to date. A replica can satisfy a read at timestamp t if t smaller than t safe. Define t safe equals the minimum of t paxos safe or t tm safe. What the hell is tm? I don't know what tm is. Where each Paxos state machine, transaction manager, where each Paxos state machine has a safe time t Paxos safe, and each transaction manager has a safe time t tm safe. T Paxos safe is simpler. It is the timestamp of the highest applied Paxos write. Because timestamps increase monotonically and writes are applied in order, writes will no longer occur at or below t Paxos safe with respect to Paxos. TTM safe is infinity at a replica if there are 0 prepared but not committed transactions. That is, transactions in between two phases of a two-phase commit. For participant slave, TM safe actually refers to a replica leader's transaction manager, whose state the slave can infer through metadata passed on Paxos writes. If there are any such transactions, then the state affected by those transactions is indeterminate. A participant replica does not know yet whether such transactions will commit. As we discussed in section 4.2.1, the commit protocol ensures that every participant knows a lower bound on a prepared transaction's timestamp. Every participant's leader for group G for transaction TI assigns a prepare timestamp as prepare IG to its prepare record. The coordinator leader ensures that the transaction's commit timestamp SI is greater than SIG prepare over all participant groups G. And therefore, for every replica in group G, over all transactions TI prepared at G. This is not making sense at all. I'm going to skip it. Section 4.1.4, assigning timestamps to read-only transactions. A read-only transaction executes in two phases: assign a timestamp, and then execute the transaction's reads as snapshot reads and sread. The snapshot reads can execute in any replicas that are sufficiently up to date. I feel like this is the simplest one. The simple assignment of sread equals tt.now.latest at any time after a transaction starts preserves external consistency by an argument analogous to that presented first writes in section 4.1.2. However, such a timestamp may require the execution of data reads at sread to block if t safe has not advanced sufficiently. In addition, note that choosing a value sread may also advance smax to preserve disjointness. To reduce the chances of blocking, spanners should assign the oldest timestamp that preserves external consistency. Section 4.2.2 explains how such a timestamp can be chosen. Section 4.2, details. That wasn't the details? Okay, this section explains some of the practical details of read-write transactions and read-only transactions elided earlier. What? As well as the implementation of a special transaction type used to implement atomic schema changes. It then describes some refinements of the basic schemes as described. Jesus freak. Section 4.2.1, read-write transactions. Like Bigtable, writes that occur in a transaction are buffered at the client until commit. As a result, reads in a transaction do not see the effects of the transaction's write. This design works well in Spanner because a read returns the timestamp of any data read, and uncommitted writes have not yet been assigned timestamps. Yeah, makes sense. Reads within a read-write transaction use wound wait to avoid deadlocks. I don't know what that is. The client issues reads to the leader replica of the appropriate group, which acquires read locks and then reads the most recent data. While a client transaction remains open, it sends keep alive messages to prevent participant leaders from timing out its transactions. When a client has completed all reads and buffered all writes, it begins two-phase commit. The client chooses a coordinator group and sends a commit message to each participant's leader with the identity of the coordinator and any buffered writes. Having the client drive two-phase commit avoids sending data twice across wide area lengths. That must be pretty subtle. A non-coordinator participant leader first acquires write locks. It then chooses a prepare timestamp that must be larger than any timestamps it is assigned to previous transactions to preserve monotonicity, and logs a prepare record through its Paxos. Each participant then notifies the coordinator of its prepare timestamp. The coordinator leader also first acquires write locks, but skips the prepare phase of the non-coordinator participant leader. It chooses a timestamp for the entire transaction after hearing from all participant leaders. Wow, so much communication. The commit timestamp S must be greater or equal to all prepared timestamps to satisfy the constraints discussed in section 4.1.3, greater than tt.now.latest at the time the coordinator receives its commit message, and greater than any timestamps the leader has assigned to previous transactions. Again, to preserve monotonicity. The coordinator leader then logs a commit record through Paxos, or an abort if it timed out while waiting on other participants. Before allowing any coordinator replica to apply after the commit record, before allowing any coordinator replica to apply the commit record, the coordinator leader waits until tt.after so as to obey the commit wait rule described in section 4.1.2. Because the coordinator leader chose S based on tt.now.latest and now waits until that timestamp is guaranteed to be in the past, the expected wait is at least 2 times epsilon bar. This wait is typically overlapped with Paxos communication. How long is Paxos communication? After commit wait, the coordinator sends the commit timestamp to the client and all other participant leaders. Each participant leader logs the transaction's outcome through Paxos. All participants apply at the same timestamp and then release locks. Jesus. Why don't you just draw me a chart or something? I don't know. Why was that all in words? Okay. There is similar detail in this stuff. I'm going to skim really quickly through the others because at this level of detail it's not really useful unless you're implementing Spanner. Section 4.2.2, read-only transactions. We referred to this section a couple or 3 times in the previous sections. Assigning a timestamp requires a negotiation phase between all of the Paxos groups that are involved in the reads. As a result, Spanner requires a scope expression for every read-only transaction, which is an expression that summarizes the keys that will be read by an entire transaction. Spanner automatically infers the scope for standalone queries. If the scope's values are served by a single Paxos group, then the client issues the read-only transaction to that group's leader. The current Spanner implementation only chooses a timestamp for a read-only transaction and a Paxos leader. That leader assigns sRead and executes the read. For single-site read, Spanner generally does better than tt.now.latest. Define last TS to be the timestamp of the last committed write at a Paxos group. If there are no prepared transactions, the assignment sRead equals last TS trivially satisfies external consistency. The transaction will see the result of the last write and therefore will be ordered after it. It makes sense. It just makes everything asynchronous. If the scope's values are served by multiple Paxos groups, there are several options. The most complicated option is to do a round of communication with all of the group's leaders to negotiate sRead based on last TS. Spanner currently implements a simpler choice. The client avoids a negotiation ground and just has its reads execute at sRead equals tt.now.latest, which may wait for safe time to advance. All reads in a transaction can be sent to replicas that are sufficiently up to date. Section 4.2.3, Schema Change Transactions. TrueTime enables Spanner to support atomic schema changes. It would be infeasible to use a standard transaction because the number of participants, the number of groups in the database could be in the millions. Bigtable supports atomic schema changes in one data center, but its schema changes block all operations. Wow, this is huge. A Spanner schema change transaction is generally a non-blocking variant of a standard transaction. First, it is explicitly assigned a timestamp in the future, which is registered in the prepare phase. As a result, schema changes across the thousands of servers can complete with minimal disruption to other concurrent activity. Second, reads and writes, which implicitly depend on the schema, synchronize with any registered schema change timestamp at time t. They may proceed if their timestamps precede t, but they must block behind the schema transaction if their timestamps are after t. Without true time, defining a schema change to happen at t would be meaningless. Well, makes it pretty easy. Section 4.2.4 Refinements. TTM safe for task manager, as defined above, has a weakness in that a single prepared transaction prevents tsafe from advancing. I don't understand that, but I'm choosing not to care. As a result, no reads can occur at later timestamps, even if the reads do not conflict with the transaction. Such false conflicts can be removed by augmenting TTM safe with a fine-grained mapping from key ranges to prepared transaction timestamps. This information can be stored in the lock table, which already maps key ranges to lock metadata. When a read arrives, it only needs to be checked against the fine-grained safe time for key ranges with which the read conflicts. Last TS, as defined above, has a similar weakness. If a transaction has just committed, a non-conflicting read-only transaction must be assigned to sRead so as to follow to that transaction. As a result, the execution of the read could be delayed. The weakness can be remedied simply by augmenting last TS with a fine-grained mapping from key ranges to commit timestamps in the lock table. We have not implemented this optimization. When a read-only transaction arrives, its timestamp can be assigned by taking the maximum value of last TS for the key ranges with which the transaction conflicts, unless there is a conflicting prepared transaction, which can be determined from the fine-grained safe time. T-Paxos safe is defined above has a weakness in that it cannot advance in the absence of Paxos writes. That is, a snapshot read at T cannot execute at Paxos groups whose last write happened before T. Spanner addresses this problem by taking advantage of the disjointness of leader-lease intervals. Each Paxos leader advances T-Paxos safe by keeping a threshold above which future writes timestamps will occur. It maintains a mapping of min-next TSN from Paxos sequence number n to the minimum timestamp that may be assigned to Paxos sequence number n+1. A replica can advance T-Paxos safe to min-next TSN -1 when it has applied through n. So it's like guessing at a thing without having the thing because of Paxos. Alright. A single leader can enforce its min-next TS promises easily. Because the timestamps promised by min-next TS lie within a leader's lease, the disjointness invariant enforces min-next TS promises across leaders. If a leader wishes to advance min-next TS across beyond the end of its leader lease, it must first extend its lease. Note that S-max is always advanced to the highest value of min-next TS to preserve disjointness. A leader by default advances min-next TS values every 8 seconds. Thus, in the absence of prepared transactions, healthy slaves in an idle Paxos group can serve reads at timestamps greater than 8 seconds old in the worst case. A leader may also advance min-next TS values on demand from slaves. Section 5. Evaluation. Alright. Hopefully this is a little bit more accessible now. We first measure Spanner's performance with respect to replications, transactions, and availability. We then provide some data on true time behavior and a case study on our first client, F1. Section 5.1, micro benchmarks. Table 3 presents some micro benchmarks for Spanner. All right, let's look at that. So we got a table here with 3 rows, replicas ID 1, 2, and 3, or 1D, 1, 3, and 5. Oh, I see. If there's 1D, and then if there's 1 replica, there's 3 replicas and 5 replicas. And then the columns, there's a latency column, and then there's a throughput column. So we talk about the latency going at about 9-ish milliseconds for 1D, and then going up to like 14 milliseconds for writes. Read-only and snapshot reads are way faster, let's say on the order of 1.4 milliseconds for each of them. Throughput, you can have 2 to 4 kops per second. Surprisingly, as the number of replicas goes up, the throughput goes up. That makes sense, but how come it goes down when it goes from 1 replica to 3 replicas? So there's some kind of trade-off effect. And throughput is way higher, of course, in read-only transactions, and even higher than that on snapshot reads. So snapshot reads you can get from 13,000 to 50,000 kops per second. That's pretty cool. So, back to reading. These measurements were taken on time-shared machines. Each span server ran on scheduling units of 4 gigabytes of RAM and 4 cores, AMD Barcelona 2200 MHz. Clients were run on separate machines. Each zone contained 1 span server. Clients and zones were placed in a set of data centers with network distance of less than 1 millisecond. Such a layout would be commonplace. Most applications do not need to distribute all of their data worldwide. The test database was created with 50 Paxos groups with 2,500 directories. Operations were standalone reads and writes of 4 kilobytes. All reads were served out of memory after a compaction so that we are only measuring the overhead of a spanner's call stack. In addition, 1 unmeasured round of reads was done first to warn many location caches. For the latency requirement, Clients issued sufficiently few operations so as to avoid queuing at the servers. From the one replica requirements, commit wait is about 5 milliseconds and Paxos latency is about 9 milliseconds. As the number of replicas increases, the latency stays roughly consistent with less standard deviation because Paxos executes in parallel at the group's replicas. Yeah, we talked about this earlier. As the number of replicas increases, the latency to achieve a quorum becomes less sensitive to slowness at one slave replica. For the throughput experiments, clients issued sufficiently many operations so as to saturate the server's CPUs. It's got a nice little chart there. Snapshot reads can execute at any up-to-date replicas, so their throughput increases almost linearly with the number of replicas. Single read-only transactions only execute at leaders because timestamp assignment must happen at leaders. Oh, it's beautiful. Read-only transaction throughput increases with the number of replicas because the number of effective span servers increases. In the experimental setup, the number of span servers equaled the number of replicas, and the leaders were randomly distributed among the zones. Write throughput benefits from the same experimental artifacts, which explains the increase in throughput from 3 to 5 replicas. But that benefit is outweighed by the linear increase in the amount of work performed per write, as the number of replicas increases. Table 4 demonstrates that two-phase commit can scale to a reasonable number of participants. So they're talking about 200 participants, and the mean latency increases to about 150 milliseconds and 320 milliseconds at the 99th percentile. It summarizes a set of experiments run across 3 zones, each with 25 span servers. Scaling up to 50 participants is reasonable in both mean and 99th percentile, and latencies start to rise noticeably at 100 participants. So they recommend 50-ish. Section 5.2, availability. So that was the first section on micro benchmarks for latency and throughput. Section 5.2 is availability. Figure 5 illustrates the availability benefits of running Spanner in multiple data centers. Kind of similar, except that the reads completed takes a hit in some of the servers. Alright. It shows the results of 3 experiments on throughput in the presence of data center failure, all of which are overlaid onto the same timescale. The test universe consisted of 5 zones ZI, each of which had 25 span servers. The test database was charted into 1,250 Paxos groups and 100 test clients, constantly issued non-snapshot reads at an aggregate rate of 50,000 reads per second. All of the leaders were explicitly placed in Z1. 5 seconds into each test, all the servers in one zone were killed. Non-leader kills, Z2, leader hard kills, Z1, and leader soft kills, Z1. But it gives no notifications to all of the servers. It gives notifications to all the servers that they should hand off leadership first. Really? Killing Z2 has no effect on read throughput. Killing Z1 while giving leaders time to hand off leadership to a different zone has a minor effect. The throughput drop is not visible in the graph, but it is around 3 to 4%. On the other hand, killing Z1 with no warning has a severe effect. The rate of completion drops to almost 0. As leaders get re-elected, though, the throughput of the system rises to approximately 100k reads per second because of the 2 artifacts of our experiment. There's extra capacity in the system, and operations are queued while the leaders are unavailable. As a result, the throughput of the system rises before leveling off again at its steady-state rate. We can also see the effect of the fact that Paxos leader leases are set to 10 seconds. When we kill the zone, the leader lease expiration times for the groups should be evenly distributed over the next 10 seconds. Soon after each lease from a dead leader expires, a new leader is elected. Approximately 10 seconds after the kill time, all the groups have leaders and throughput has recovered. Shorter lease times would reduce the effects of server deaths on availability, but would require greater amounts of lease renewal network traffic. We're in the process of designing and implementing a mechanism that will cause slaves to release Paxos leader leases upon leader failure. Wow, that's pretty cool. I wonder if they did that. Section 5.3, True Time. 2 questions must be answered with respect to true time. Is epsilon truly abound on clock uncertainty, and how bad does epsilon get? Yeah. For the former, the most serious problem would be if a local clock drift would greater than 200 microseconds per second. That would break assumptions made by true time. Our machine statistics show that bad CPUs are 6 times more likely than bad clocks. That is, clock issues are extremely infrequent, relative to much more serious hardware problems. As a result, we believe that TrueTime's implementation is as trustworthy as any other piece of software upon which Spanner depends. Figure 6 presents TrueTime data taken at several thousand span server machines across data centers up to 2200 km apart. It plots the P90, P99, and P999 percentiles of epsilon, sampled at time-slave daemons immediately after polling the time masters. The sampling elides sawtooth in epsilon due to local clock uncertainty, and therefore measures time master uncertainty, which is generally 0, plus communication delay to the time masters. The data shows that these two factors in determining the base value of epsilon are generally not a problem. Okay. However, there can be significant tail latency issues that cause higher values of epsilon. The reduction in tail latencies beginning on March 30th were due to networking improvements that reduced transient network link congestion. The increase in epsilon on April 13th, approximately 1 hour in duration. I see there. So the figure 6 has some spikes that he's talking about. The increase in epsilon on April 13th, approximately 1 hour in duration, resulted from the shutdown of 2 time masters at a data center for routine maintenance. We continue to investigate and remove causes of true time spikes. Section 5.4, F1. Spanner started being experimentally evaluated under production workloads in early 2011 as part of a rewrite of Google's advertising backend called F1. This backend was originally based on a MySQL database that was manually sharded in many ways. The uncompressed dataset is tens of terabytes, which is small compared to many NoSQL instances, but was large enough to cause difficulties with sharded MySQL. The MySQL sharding scheme assigned each customer and all related data to a fixed shard. This layout enabled the use of indexes and complex query processing on a per customer basis, but requires some knowledge of the sharding in business application logic. Resharding this revenue critical database as it grew in the number of customers and their data was extremely costly. The last resharding took over 2 years of intense effort and involved coordinating and testing across dozens of teams to minimize risk. This operation was too complex to do regularly. As a result, the team had to limit growth on the MySQL database by storing some data in external big tables, which compromised transactional behavior and the ability to query across all data. The F1 team chose to use Spanner for several reasons. First, Spanner removes the need to manually reshard. Second, Spanner provides synchronous replication and automatic failover. With MySQL master-slave replication, failover was difficult and risked data loss and downtime. Third, F1 requires strong transactional semantics, which made using other NoSQL systems impractical. Application semantics requires transactions across arbitrary data and consistent reads. The F1 team also needed secondary indexes in their data, since Spanner does not yet provide automatic support for secondary indexes, and was able to implement their own consistent global indexes using Spanner transactions. All application writes are now by default sent through F1 to Spanner, instead of the MySQL-based application stack. F1 has 2 replicas on the west coast of the US and 3 on the east coast. The choice of replica sites was made to cope with outages due to potential major natural disasters and also the choice of their front-end sites. Anecdotally, Spanner's automatic failover has been nearly invisible to them. Although there have been unplanned cluster failures in the last few months, the most that the F1 team has had to do is update their database schema to tell Spanner where to preferentially place Paxos leaders, so as to keep them close to where their front ends moved. Spanner's timestamp semantics made it efficient for F1 to maintain in-memory data structures computed from the database state. F1 maintains a logical history log of all changes, which is written into Spanner itself as a part of every transaction. F1 takes full snapshots of data at the timestamp to initialize the data structures and then reads incremental changes to update them. Table 5 illustrates the distribution of the number of fragments per directory in F1. Let's look at table 5. So 1 fragment over 100 million directories, 100 fragments, 7 directories. I don't know what that means. Each directory typically corresponds to a customer in the application stack above F1. The vast majority of directories, and therefore customers, consist of only one fragment, which means that reads and writes to those customers' data are guaranteed to occur on your own single server. The directories with more than 100 fragments are all tables that contain F1 secondary indexes. Writes to more than a few fragments of such tables are extremely uncommon. The F1 team has only seen such behavior when they do untuned bulk data loads as transactions. Table 6 presents spanner operation latencies as measured from F1 servers. Replicas in latency goes from 8 milliseconds at a mean to 100 milliseconds for multi-site commits. But standard deviation is very high. 376 standard deviation for mean read latency, and 50 standard deviation for the multi-site commits. So let's talk to see why. Replicas in the East Coast data centers are given higher priority in choosing Paxos leaders. The data in the table is measured from F1 servers in those data centers. The large standard deviation in the write latencies is caused by a pretty fat tail due to lock conflicts. The even larger standard deviation in read latencies is partially due to the fact that Paxos leaders are spread across 2 data centers, only one of which has machines with SSDs. In addition, if the measurement includes every read in the system from 2 data centers, the mean and standard deviation of the bytes read were roughly 1.6 kilobytes and 119 kilobytes. Alright, section 6, related work. Consistent replication across data centers as a storage service has been provided by Megastore and DynamoDB. DynamoDB represents a key value interface and only replicates within a region. Spanner follows Megastore in providing a semi-relational data model and even a similar schema language. Megastore does not achieve high performance. It is layered on top Bigtable, which imposes high communication costs. It also does not support long-lived leaders. Multiple replicas may initiate writes. All writes from different replicas necessarily conflict in the Paxos protocol, even if they do not logically conflict. Throughput collapses on a Paxos group at several writes per second. Spanner provides higher performance, general-purpose transactions, and external consistency. Pavlo et al. Have compared the performance of databases and MapReduce. They point to several other efforts that have been made to explore database functionality layered on distributed key-value stores as evidence that two worlds are converging. We agree with the conclusion, but demonstrate that integrating multiple layers has its advantages. Integrating concurrency control with replication reduces the cost of commit weight in Spanner, for example. The notion of layering transactions on top of a replicated store dates as far back as Gifford's dissertation. Scatter is a recent DHT-based key-value store that layers transaction on top of consistent replication. Spanner focuses on providing a higher-level interface than Scatter does. Gray and Lamport describe a non-blocking commit protocol based on Paxos. Their protocol incurs more messaging costs than two-phase commit, which would aggravate the cost of commit over widely distributed groups. Walter provides a variant of snapshot isolation that works within, but not across data centers. In contrast, our read-only transactions provide a more natural semantics because we support external consistency over all operations. There has been a spate of recent work on reducing or eliminating locking overheads. Calvin eliminates concurrency control. It pre-assigns timestamps and then executes the transactions in timestamp order. HStore and Granola each supported their own classification of transaction types, some of which could avoid locking. None of these systems provides external consistency. Spanner addresses the contention issue by providing support for snapshot isolation. VaultDB is a sharded in-memory database that supports master-slave replication over the wide area for disaster recovery, but not more general replication configurations. It is an example of what has been called NewSQL, which is a marketplace push to support scalable SQL. A number of commercial databases implement reads in the past, such as MarkLogic and Oracle's Total Recall. Lomit and Lee describe an implementation strategy for such a temporal database. Farsight derived bounds on clock uncertainty, with much looser than true times, relative to a trusted clock reference. Server leases in Farsight were maintained in the same way that Spanner maintains Paxos leases. Loosely synchronized clocks could have been used for concurrency control purposes in prior work. We have shown that true time lets one reason about global time across sets of Paxos state machines. We have spent most of the last year working with the F1 team to transition Google's advertising backend from MySQL to Spanner. We're actively, this is section 7, future work. We're actively improving its monitoring and support tools, as well as tuning its performance. In addition, we have been working on improving the functionality and performance of our backup and restore system. We're currently implementing the Spanner schema language, automatic maintenance. We're currently implementing the Spanner schema language, automatic maintenance of secondary indices, and automatic load-based resharding. Longer term, there are a couple of features that we plan to investigate. Optimistically, doing reads in parallel may be a valuable strategy to pursue, but initial experiments have indicated that the right implementation is non-trivial. In addition, we plan to eventually support direct changes of Paxos configurations. Given that we expect many applications to replicate their data across data centers that are relatively close to each other, true time epsilon may noticeably affect performance. We see no insurmountable obstacle to reducing epsilon below 1 millisecond. Time master query intervals can be reduced, and better clock crystals are relatively cheap. Time master query latency can be reduced with improved networking technology, or possibly even avoided through alternate time distribution technology. Finally, there are obvious areas for improvements. Although Spanner is scalable in the number of nodes, the node local data structures have relatively poor performance on complex SQL queries because they were designed for simple key value accesses. Algorithms and data structures from DB literature could improve single node performance a great deal. Second, moving data automatically between data centers in response to changes in client load has long been a goal of ours. But to make that goal effective, we'll need the ability to move client application processes between data centers in an automated and coordinated fashion. Moving processes raises the even more difficult problem of managing resource acquisition and allocation between data centers. Section 8, Conclusions. To summarize, Spanner combines and extends on ideas from two research communities. From the database community, of familiar, easy-to-use semi-relational interface transactions, and a SQL-based query language. From the systems community. Let me try that again. From the database community, a familiar, easy-to-use semi-relational interface, transactions, and SQL-based query language. From the systems community, scalability, automatic sharding, fault tolerance, consistent replication, external consistency, and wide area distribution. Since Spanner's inception, we've taken more than 5 years to iterate to the current design and implementation. Part of this long iteration phase was due to a slow realization that Spanner should do more than tackle the problem of a globally replicated namespace, and should also focus on database features that Bigtable was missing. One aspect of our design stands out. The linchpin of Spanner's feature set is true time. We have shown that reifying clock uncertainty in the time API makes it possible to build distributed systems with much stronger time semantics. In addition, as the underlying system enforces tighter bounds on clock uncertainty, the overhead of the stronger semantics decreases. As a community, we should no longer depend on loosely synchronized clocks and weak time APIs in designing distributed algorithms. Published in the Proceedings of OSDI 2012. That's pretty cool. Just a longish paper, and a lot of detail where I'm not exactly sure it's needed, like you're proving stuff that is obvious to you, that I don't necessarily care about because I just want to know how you work. And yeah, that's Spanner. What do I think about this? I don't think I did a very good job of like comparing. You'd have to have a pretty strong background in the other papers as well to really understand the novelty of this. Obviously, it did a good job of explaining the TrueTime API and the rough architecture of Spanner and some of the limitations. Some of the things that they still want to do but haven't done yet. Understanding the design goal is really important. It's scalable, multi-version, globally distributed, and synchronously replicated. I think the multi-version is just referencing timestamps. I wonder what the garbage collection is talking about. And I don't know. It seemed like they were talking about stuff like automatic rebalancing of shards or fragments. And then they said they hadn't done that yet. So I'm not really sure how much they had done at this publication. What is synchronously replicated? So I guess that's the Paxos stuff. But it's pretty clear how they support externally consistent distributed transactions. So I mean, for all of that, I think it's great. It makes me scared to use read and write together because it's so expensive. But the benchmarks went a long way towards helping me be reassured that, like, yeah, it's expensive, but it's not terrible. So yeah, that is the Spanner paper. I don't really have any other comments apart from, like, obviously this is a foundational paper in the literature of distributed systems. This is my first one. It was a heavy read, but hopefully I'll try and get better as I read more. Borg paper, the TCP spec, and B-tree paper. Okay. All right. Thanks for joining. Bye.